Hello everyone. We will discuss Codeforces Div 3 of today. So let's start. This is the first question. Here we are given a farmland where Shizuku counts n legs and it is known that only chickens and cows live in the farm. A chicken has 2 legs while a cow has 4 legs. Now we need to find the different configurations of Farmer John's farm that are possible. That is how many different number of ways the legs can be divided into chickens and cows. Chickens and cows. And chicken has 2 legs, cow has 4 legs. Alright. And we are given that there are total n legs. Okay. So if we fix one of them, like let's say fix chickens, let's say we are having x number of chickens, then legs denoting chickens would be equal to 2 times x. Now the remaining legs is equal to 2n minus 2 into x, which belongs to cows. So if this particular term is valid, this is a valid configuration, when will this term be valid? This is a multiple of 4. Alright, then it is a valid configuration. And we need to count of all such configuration. Alright. So for that, we need to first fix x. So what is the value of n? N is up till 100 and t cross 100 would be 1e4, which is computable in 1 second. So we can compute for all possible values of x and find if this particular x is a valid x. If it is, add 1 to our count of configurations. At the end, print what are the number of possible configurations. So let's implement the problem. We need to take input the number of legs. Now iterate over the possible values of x, or let's say legs denoted with chicken. Since chicken has only even number of legs, like that is 0, 2, 4, 6. These all numbers denote the legs of chicken. Now the remaining legs is equal to n minus I, and it should be multiple of 4. Then this is a possible configuration. Alright. And this passes our solution. Let's move to the second problem. In this problem, we are given a non-negative integers, an array consisting of non-negative integers, where some of the elements are -1. Now, we would like to fill the blanks element with some non-negative integers such that the absolute value of sum of elements in its difference array is minimized. So what is a difference array? Difference array is defined as the difference of consecutive or adjacent elements inside the array. Alright, so let's understand it. Let's say we had an array A1, A2 up till AN. Now we need to build the difference array. What would it be? It is equal to A2 minus A1 A3 minus A2 up till an minus an minus 1. Alright, so how many elements are there? There are total n minus 1 elements in the difference array. And what do we need to do? We need to minimize the absolute value of sum of b. Alright, so what do the sum of b look like? Let's write it down. It is a2 minus a1 plus a3 minus a2 plus a4 minus a3 up till an minus an minus 1. Alright, this a2 gets cancelled out with this a2, this a3 cancels out with this a3. Similarly, this an minus 1 cancels out with some n minus 1 present above. So what is the remaining elements? If we see, an is remained and a1 is remained. So this is sum of b, and we need to minimize absolute value of sum of b. It is equal to absolute value of an minus a1. So what can we do if we are given that a1 and an are both equal to minus 1? Then just initialize a1 equal to an equals to 0. Alright. If an or a1 is minus 1, what happens in this case? The one that is minus 1 is equal to the other one now. Alright, because this is the only scenario we have. And what about other indices that are minus 1 equals to 0 now? Alright, so let's implement what we have observed till now. So take the array's input. Now, if the zeroth element equals to minus 1 and the last element equals to minus 1, what we say? The zeroth element equals to the last element, which is equal to 0. Why? Because we want the lexicographically smallest array. Now, what if one of the element, let's say if zeroth element is minus 1 and the last is not, then zeroth element equals to the last element now, because that is how the absolute value will be equal to 0. Alright. And the other scenario, the last element is equal to minus 1. So the last element equal to the first element now. What in the other scenario? In the other scenario, the sum cannot be minimized or cannot be changed. So it will remain as such, but we want the lexicographically smallest array. So for rest of the indices, we just print 0 instead of minus 1. If the current element is equal to minus 1, print 0. And if it is not, print vec and type. So this is it. This passes our test cases and accepted solution. Let's move to the next problem now. In this problem, we are given a game played by Aji Sai and Mai. Both of them have an array denoted as A and B respectively, and the array is consisting of only zeros and ones. The game lasts for n turns, where the odd turns are played by Aji Sai and the eventh term is played by Mai. On the ith term, the player to move may choose to swap AI and BI. That is, in the ith turn, if I is odd, Aji Sai can choose to swap AI and BI, and if I is even, Mai can choose the same. At the end, Aji Sai achieves the score which is equal to XOR of all the elements present in A. Similarly, Mai achieves the score XOR of all the elements present in B. Alright. At the end, if the game is played optimally, we need to print if Aji Sai wins or Mai wins or it is a tie. So let's observe the game. Let's say this is the array. Array consists of some numbers and the last number is 1 for A and 0 for B. What happens here? If XOR of elements present in prefix is equal to 1, what will Aji Sai do? Let's say I is odd now. Aji Sai will just swap it. Why? Because XOR of ones and zeros is 1 only if number of ones are odd. How do we come at this observation? Because XOR of A and A equals to 0. So if there are even numbers of A, XOR is equal to 0. And if there are odd numbers of A, then the XOR is equal to A itself. Alright. So at the end, if there is a choice of 1 and 0, the current player will see whether its prefix contains of odd number of ones. If it contains of odd numbers of ones, it will swap. So that at the end, the number of ones is equal to even or let's say odd. Alright. And if it is even, he will try to make it odd by swapping. The person at last choice of 0, 1 or 1, 0 type has the option to choose make its XOR 1. Alright. So that person is the deciding factor of the game. Alright. But will that person always win? The answer is no. Why? Let's see a scenario. Let's say there are A's and B's as such. Before the fourth index where my choose, the XOR from 1 to 3 is 1, and for B, XOR from index 1 to index 3 is 0. Okay. Uh, what happens if my choose to swap? Now the XOR becomes 0 for both of the cases. And what if my do not choose to swap? The XOR is 1 for both of the cases. Okay, so this leads to a tie. So we need to consider that if the last person can lead to winning the game, he wins. Otherwise, the game is tied. Alright. So, how would we decide who wins if it is not a draw? If the last index of 1 0 or 0 1 type is odd, then Maritai wins or Mai wins. Alright. Alright. And when is the game draw? Let's understand this. Let's say initially the number of ones in A, count of ones in A equals to odd, and count of B in count of ones in B is equal to odd as well. Now if there is a swap of one ones in both of them, like let's say 1 1 move from A to B, then this become even and this become even as well. Alright. In the above scenario, if there is no swapping of ones, then answer is 1 for both of the cases. And if there is one swapping, answer is 0 for both of the cases. Alright. So, what is the other case? If count of A is even and count of B is even again, then we have even and even number. If we choose 1 1 from first array and move it to the second array, now both of them becomes odd. Alright, and both of them gives XOR as 1. This again leads to a draw. So we come to a conclusion that draw can only be obtained if count of ones in A has same parity as count of ones in B. Else, the person with last choice of 1 0 or 0 1 type is the one who wins. Alright, let's implement this. Okay, so we had A and B as our arrays. Let's keep it one based indexing. So we have our arrays A's and B's. Now, what do? We calculate count of ones in A and count of ones in B. All right. What is the scenario for a tie? If count A modulo 2 is equal to count B modulo 2. So they have same parity. Both of them are even or both of them are odd. Then it's lead to a tie. All right. Else, see from back, where is the first place where there is 1 0 or 0 1 type. If it is, then check what is the parity of current index. If it is odd, then Aji Sai wins. Else, Mai wins. Alright. And this is our solution. Okay. If we get such a scenario, no need to check any further. Just we conclude that this leads to end of the game. Alright. Let's move to the next problem or hard version of this problem. In this version, the values of AIs and BIs can be up till 1e16. Alright. So what is the change in a problem? Let's see one proof here. Okay. One proof or one mathematical identity. Alright. The identity is 2 to the power I is always greater than sum 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 up till 2 to the power I minus 1. Alright. How is it so? Let's understand it with example. Like uh, 2 to the power 3 is 8. And what is 2 to the power 2? It is 4. 2 to the power 1, it is 2. And 2 to the power 0, it's 1. What is the sum? It is exactly equal to 7. Alright. And 8 is greater than 7. We use this identity in our problem. How? Okay. If a person sets ith bit, should we consider, let's say, if A sets ith bit and B cannot. So should we consider rest bits or I minus 1, I minus 2 up till 0th bits? We can conclude it from here. If A has this bit set and B does not have, then for this example, A has 8 in its answer. And in the worst case scenario, B will have all of them while A will not. Alright, B has 4, 2, 1, everything in its set bit, and A do not. But still, we conclude that here A wins because it has 8. Alright, So we conclude that if A, a person has a bit set, then the opponent do not. Then the bits, smaller bits, should not be considered. Alright. Now this problem again changes to the previous problem, just with bits. Iterate over bits from large to small. Alright. First 31st bit, then 30th, then 29th, and so on. If this bit can be set by one of them and not by other, then the player wins. Alright, so let's implement it. Let's have the solution of C1 and modify it to solution of C2. What did we say? We do the same thing but for each bits. Alright. And if the current bits have same parity, then it leads to a tie at the current index. Alright. So there is a possible scenario that the up player can set a bit which is smaller than the current bit later on. So we do not conclude that it leads to a tie, but rather we need not do all these computations to find the first non-matching bit. At the end, if no one could win, then it means that this particular scenario has run everywhere. Alright, so what do? We say that since all the bits cannot lead to a winner, then it is a tie. Alright, so we need to first check all the bits now. Let's denote the current bit as B. Alright, we have a array B and a bit B. So we need to change the name. Let's denote bit as BT now. Now let's run our code. Okay. Okay, so there is a problem in comparison and precedence of operators. So this bracket needs to be closed here, and If we run it now, this passes. So let's move to the next problem. Okay. So we are given a permutation of length n. We need to determine if there exists an undirected tree with n vertices labeled from 1 to n satisfying the following condition. Let u and v be two vertices connected by an edge. Then u appears before v in P. Alright. So we are given a permutation. We need to find a tree where for all the nodes from for all the edges of form u comma v, the smaller number appears before the larger number in our permutation. For example, if we had the first test case as our permutation. Alright. So we can have a edge 1 comma 3, we can have a edge 1 comma 4, we can have a edge 3 comma 4, but we cannot have a edge 5 comma 2. Why? Because 5 appear before 2 in our permutation. Alright. And we need to construct such a tree where every edge satisfies this particular condition. So let's write down all the observations. The first observation is that edge has, okay, a tree has n minus 1 edges. Alright. So if by any way we can make n minus 1 edges such that it do not lead to a cycle, it means we can make a tree. Alright. So what is the second observation? Second observation is that for a tree, there should be only one connected component. Alright. And there should not be, how to avoid a cycle. There should not be a edge between two nodes in the same connected component. Alright. So we can use DSU to make sure that we are framing a single connected component at the end which leads to a tree and there is no cycle in that tree. Alright. What is the third observation? In the third observation, what do we see? If a node or let's say number before index I is smaller than P at I, then we can make a edge from Pi to Pj. Let's say the index if a index j is smaller than pi, pj is smaller than pi, and j is smaller than I, then we can make a edge from pi to pj. All right. So let's create a set of connected components first. Like for example, in this test case, let's create the maximum number of connected components that are for sure free with cycles. We can connect one with three. All right. Then one with, okay, let's visualize it in the form of tree. We can connect one with three, then one with four. All right. Then again, then one with five. Now, can we connect one with two? No. All right, all right. We can connect one with two as well. Okay. And then one with six again. Then again a edge, let's say six. All right. So first case, the test case is simple enough. Now let's move to another test case. Let's say this one. So let's create the maximum number of connected components first. We can connect two with four, all right, and two with six. Now, can we connect two with one? No, because this is an inversion. Like two is greater than one. So this would lead to conflict in this scenario, this condition. So one should be a different connected component itself. Now, what are the neighbors of one? It is 3 and 5. Now, we have two connected components and we want a single tree. So these two connected components should be joined using a edge. What is the best possible way for it? Okay, this leads to two connected component, that is 246 and 135. If we note that when do we lead to a new connected component? When if we start with 2 and we get greater number than 2, then it is fine. This leads to a single connected component. If we see a smaller number than 2, then this leads to a new connected component to obey this particular condition. Now, if we want that this should be a tree, one of the elements in this connected component should have a edge with one of the elements in this connected component. So how is this possible? Can this 5 have a edge with this 2? Yeah, for sure. Because 5 is greater than 2. So create a edge between 5 and 2. Now let's say we want to create a edge between these two connected components. What is the best possible scenario for it? take the largest element of this connected component, that is the later connected component, and the smallest element of former connected component, because we know that all the elements present before this 5 are smaller than 5, and all the elements present in after this 2 are greater than 2. So if this 5 is greater than this 2, there can be a edge. But if it is not, the smallest element of this component is greater than largest element of this component. So this leads to a scenario when edge cannot be formed. And at the end, if we can combine all of the connected component like this, we say that we can form a tree. If not, we say that we cannot form a tree. So let's go on and implement this. First of all, we would be needing a template of disjoint set union. So let's copy it for now. Okay, so let's now make a set of all the nodes. All right, this SZ is a predefined template. So in order to remove this error, let's comment that. Okay, and we have defined N as 2e5. What is the requirement? It is 2e5. The number of nodes can be up till 2e5. Now we have all the nodes. First, create a connected component like we did before. All right. So we have a prefix. Let's denote it as the first node. Now from the second node, if we find that prefix is smaller than current array, then take a union. All right. We are creating the connected components like we did here. The first connected component 246 and second connected component 135. And in the else part, our current element is smaller. I mean, uh, the current element is greater. Okay, so the current element is smaller. Like here, 1 was smaller than 2. So this becomes the new leader of connected component now. So this is it. Now, what about the suffix part? For each of these components, we need to have the track of largest element, and for the component under consideration, we need to have the track of smallest element. So how to do that? For the previously used components, have a track of largest element, not for the currently used connected component. All right. So let's define it, the suffix or the maximum calculated up till now as 0. In the current component, the maximum is 0. And the connected component of previous largest element of the previous connected component, that also has 0. Now iterate from backward. Okay. If we find that we got a new connected component, if we find that we got a new connected component, then our suffix is maximum of previous uh, components maximum value. All right. Like if we moved from this particular part 135 to 246, then this particular component we need to find the maximum. While moving to this part, we need to have the max of this particular component. So when we move to this particular component, we said what was the max of previous component. It is contained in cur. Now what about the uh, representative of current component? It is given by find set. All right. Now when do we create a edge? When the current element is smaller than the largest of previous element or previous connected component. And when do we create a edge? We create a edge when they both do not belong to same connected component in order to avoid cycles. All right. And at the end, what is the maximum of current component? Take it the max with current element. Now, how to check if we have framed a tree or not? If all the elements belong to same connected component, then we can say it is a tree. If not, we can conclude that we have failed and a tree cannot be formed. All right, let's run the code. All right, we have passed all the test cases and this solution is accepted. Now, for the hard version of this problem, we need to also print the tree in the form of edges. So just add the places where we have added a edges. So how do we represent a edge? It is in the form of vector of pair. All right. And since here we added a edge, we say we inserted pref and vec. All right. There is a edge between the previous element or prefix minimum and current element. Here also we have added a edge. So just push it inside our array. All right. So at the end, we also need to print all the edges. So just print them. So this is it. This passes the solution. For the first test case, it is yes. For second, it is no. Third is no. Fourth is yes. Then no. Then yes. Then yes. Yes. All right. So this passes, and we have completed the discussion for Div 3 today. All the best for upcoming contests.